Hey there, welcome to another video. So this video is all about putting together the ideas of the last like 4 or 5 videos. We are going to just basically be practicing. I'm going to give you an outline of structure on how to find all the asymptotes and holes in a function. We're going to basically do 6 examples as fast as I can while still explaining the concepts, but I'm not really teaching you anything new that we haven't done, just the order in which you go to make this the most efficient. Can you go out of order? Yes, but I found that this order really keeps things structured well and limits the amount of work that you have. Next video, longest video in this series is going to be practicing graphing this. So right now, this would be like the first few steps in how to graph rational functions. So here's what we're going to get into. What I expect you to learn from this is how to appropriately find a horizontal asymptote, an oblique asymptote, vertical asymptote, and holes if they exist. So we're going to put all that together. So the first thing we want to do, find your end behavior first. Your end behavior includes either a horizontal asymptote or an oblique asymptote or just straight up end behavior. You're not going to have all of them, just one of them. We're going to use leading terms to do that. After you've done that, then factor. The reason why we do the end behavior first is typically your rational functions come as polynomials in that standard form first, and it's easiest just to find your leading terms rather than having to factor, then redistribute, or go backwards. We really don't want to have to do that. So I'm making this in order for you. After that, we factor. Great. Define your domain. Say what x values can't happen, and then say how they can't happen. That would be determine whether your domain issues create a vertical asymptote or a hole, whether or not you can cross out that factor or not, and then determine where that hole is if you have to. If there is a hole, you need to find kind of the point that's missing, and we're going to use that graphically in the next video. And if you have a vertical asymptote, whether that is even or odd based on the multiplicity. So we're going to get right into it. Again, I'm going to be going very quickly. I'm teaching you this lesson on the assumption that you've watched the last few videos and you know how to find a horizontal, oblique, or asymptote, or end behavior, and vertical asymptote if one exists. So let's go here. The first thing we're going to do with any function, if it's not already factored, is we're going to find the end behavior. So when we look at end behavior deals with the leading terms of your polynomials, both the numerator and denominator. Because they are power functions, your variables, at least on one of the numerator and denominator, will always cancel out fully. In this case, they both do. And if we think back to a horizontal asymptote, the first thing you might do is go, oh yeah, hey, those have the same degree. I am going to have a horizontal asymptote at the leading coefficients. In other words, 3/1. We can see that by end behavior. I always show end behavior every single time because by simplifying, you are going to find either a horizontal asymptote or an oblique asymptote or end behavior every time. You just have to interpret it. So in this case, you go, yeah, you're just going to get 3. What does that mean? That means you are going to have a function that gets toward y = 3 as you approach positive and negative infinity. That's a horizontal asymptote at 3. So that's pretty much done. So all right, that's great. If you want to just do the kind of the, I don't know, Cliff Notes version of it, you look at your degrees. If they're the same, take your coefficients, and that's your horizontal asymptote. If your degrees are the same, you're going to get a horizontal asymptote at the leading coefficients. If not, you either have a numerator that has a higher degree or denominator. Numerator higher, you get oblique asymptote or end behavior that's not one of these two things. If the degree and the denominator is higher, you get a horizontal asymptote at 0. So we'll talk about that in just a minute. All right, the next thing we would do is factor. Now, when we look at the numerator and the denominator, this is already factored completely. So 3x + 5 is linear and x - 6 is linear. I'm going to do this just to make sure that we see that is one factor. And then we're going to set our factors on the denominator equal to 0 to see what our domain restrictions are. So we go, all right, x - 6 is our only factor. If I add 6, we'd say, well, x = 6. X = 6 is a problem, so x = 6 is something that I need to restrict. You see, if I allow x to equal 6, I get 0 on the denominator. That's a big issue. That's undefined. So we say on our domain is any number except for 6. We can't allow that. Now we determine how we can't allow it. This is either going to create a hole at x equals 6 or a vertical asymptote at x equals 6. So, and remember, you need to know about vertical asymptotes from a previous video. So we do this. It's all stuff we've done before. We go, all right, our factor equals 0 by the zero product property. We know that we're defining our domain. Denominators cannot equal 0 or we have undefined values. This is an undefined value, so we cannot allow x equal 6. Now, what that creates for us depends on whether the factor that gives us this undefined value can be canceled, therefore creating a hole, or can't be canceled, therefore creating a vertical asymptote. So we look at x minus 6. Can you cancel that factor with something on the numerator? No. Then at x equals 6, we have an undefined value, but at x equals 6, that undefined value is created for us a vertical asymptote. So this is what we can't have, and what we do next is how we can't have it. It's kind of a weird statement. It's either going to be a missing point, we don't have anything there, or a vertical asymptote, we don't have anything there. Just two different things. So at x equals 6, we have a vertical asymptote, kind of like a force field, vertical force field, and we're going to define whether or not that is an even or an odd vertical asymptote. And that depends on what our multiplicity is for that factor. We're going to get odd or even, depending on what that power is, which is why we put in parentheses to create a factor. Well, that power is 1, so that would be an odd power or odd multiplicity vertical asymptote. And that tells us that this vertical asymptote is going to look like this or like this, depending on some signs, and we deal with that in the next video. So we've done it, we go, okay, end behavior, we have a horizontal asymptote at 3. We've looked at our powers, determined that we were going to have a horizontal asymptote at leading coefficients. We found that by taking our leading terms and simplifying, or just recognizing kind of that shortcut, y equals 3 is our horizontal asymptote. We defined our domain and then said what that's going to give us. This is the first few steps on how we graph rational functions. Let's go ahead and let's deal with our next example. So next example, we're going to do the same thing, just very quickly. The first thing we're going to do is find end behavior. How we do that, and I do this every single time. I take my first two terms, my leading coefficients of the numerator and denominator respectively, and we make a ratio. And because those are always power functions, your variables on either the numerator or denominator or both are going to disappear. In this case, we know that we can simplify and get 1 over x. Now think critically about it. What is going to happen at the ends of your functions? Think back to the video horizontal asymptote. Well, as x gets positive or x gets negative, 1 divided by really big positive numbers or really big negative numbers, a limit idea, 1 divided by really big values, either positive or negative, is getting close to 0. This is going to have a horizontal asymptote at y equals 0. We learned that in horizontal asymptotes, that if your degree of your denominator is larger than your numerator, you will have a horizontal asymptote at y equals 0. So as x gets bigger, this function approaches 0. I'm not going to write out that limit. I did that on that video. As x approaches positive infinity, g of x approaches 0. And as x approaches negative infinity, well, g of x still approaches 0 just from positive and negative places. That's what we're doing. So we will have a horizontal asymptote at y equals 0. The degree of the denominator is larger than the numerator. It outpaces it. So we'd have constant over some number getting really, really big. That's getting close to 0. After that, we have to factor everything. Now, the numerator is factored, but that x to the 4th minus 1, we've seen that a couple times. That's like a difference of squares wrapped up in another difference of squares. So I'm going to take a moment and think of this as x squared squared. So x squared squared minus 1 squared would give us x squared minus 1 and x squared plus 1. But that's also a difference of squares. This one's not. That's an irreducible quadratic. You cannot factor it anymore. That is done. But this is a reducible quadratic. You can factor that as x minus 1 and x plus 1. So our function becomes x cubed already factored, over x minus 1, x plus 1, and x squared plus 1. Now, if you remember doing this exact factoring was in, well, it was when we talked about complex solutions to these polynomials. We are not worried about complex solutions when we are graphing polynomials or rational functions. They're not going to create anything for us. They just kind of hang on in this class. Calculus 1, they typically will create some sort of a turning point or local maximum, local minimum that doesn't interact with your x-axis. So that's typically what they do. So in our case here, we go, okay, we've already found our end behavior. Notice it's a lot easier to find end behavior here than it would be from a factored polynomial or factored rational function. This you'd have to redistribute, or at least fake distribute. If you remember that x times x squared is x to the fourth, you'd have to do that again. So that's kind of annoying. That's why we do end behavior first. Now that we have everything factored, we're going to define our domain. So our domain says, hey, look at your denominator. Take all the factors that are there and set them equal to 0. All right. So we know that if our denominator equals 0, that's a problem. So x minus 1 equals 0 would create a problem for us, an undefined value of x based on the zero product property of setting your denominator equal to 0. Same thing with x plus 1. Now, x squared plus 1 equals 0. That would be another factor set equal to 0 by the zero product property, but this is not possible to solve over the real number system. So this basically gives us nothing that we have to worry about as far as our domain. Here's the point. You can't plug in a real number, square it, add 1, and get 0. That's impossible. So that's not giving us any sort of domain restrictions in the real number system, which is how we were graphing. So this basically does nothing for us. These two, however, if we add 1 and subtract 1 respectively, this is giving us some values that are causing zeros on our denominator. If I plug in 1, that's 0 times, I don't care. And plug in negative 1, that's 0 times, I don't care. It's going to give you 0 on the bottom of your fraction. It's a problem. So our domain says you need to restrict those. Those are two values that you can't have. Now, how can't you have them? Do they create a hole at those values of x, or do they create a vertical asymptote? We look back at our factor for that. So we look back at, here's 1 came from x minus 1, the factor. That said, hey, if I can cancel out x minus 1, that's a hole, or a removable discontinuity is another way to say that. If you can't, that's a vertical asymptote. There's nothing on our numerator to cancel that factor. So this is defining a vertical asymptote at x equals 1. That can be kind of confusing, the notation. You're saying, wait a minute, I thought x can't equal 1. It can't. So at x equals 1, we have something that you cannot allow. And that's what we're saying here. At x equals 1, you have a vertical asymptote. That's a disallowed value of x. That's why we define it that way. It's kind of like saying, hey, at x equals 1, that vertical asymptote says, yeah, you can't have 1. You can't let the function have an x value of 1. It's just showing how we're disallowing it. So at x equals 1, we have a vertical asymptote, and we look back at the exponent of the factor that's giving us that vertical asymptote. It's 1. That means that it's odd. 1 is an odd number, and you're either going to do this or this. Odd means opposite infinities. The same exact thing happens at x equals negative 1. At x equals negative 1, we cannot allow that x value. So we look back at the factor that's giving us that. I can't cancel it. That means that at x equals negative 1, we have another vertical asymptote. It also has an exponent of 1, meaning that's odd. So we're going to have a kind of an interesting graph here. This doesn't do anything for us as far as a vertical asymptote or a hole, because this can't equal 0. So it's not creating a domain problem for us. Domain problems are what gives us those graph issues of vertical asymptote or hole. So in our case, we're going to have a horizontal asymptote at y equals 0. That's the x-axis, and we'll have two vertical asymptotes. Okay. You can cross a horizontal, but you can't ever touch a vertical. That's why they're undefined, and we're sort of saying how they're undefined. So we'll have this at end behavior, and we'll have vertical asymptotes in the middle at 1 and -1. So this graph, and they're odd. So this graph does something like this or this, and something like this or this at both of those asymptotes because they are odd. That's what I need you to focus on and get out of this lesson, is what we're doing and the structure of how we're doing it. We have 4 more examples. Again, I'm going to go quite quickly through them. I'm going to start showing you what would happen if we have a numerator larger than a denominator, whether we have an oblique or just end behavior. So we'll get to that in just a second. All right, let's get right to it. So we got a couple more examples. Let's take a look at g of x. We are always going to find end behavior first on our rational functions if they come in standard form, which is everything that's distributed. If not, we have a chance to go out of order, but we're going to get to that when we start graphing rational functions. That's kind of the exception to the rule. So we're typically going to start by having a distributed or standard form rational function, and we're going to find end behavior. We look at our leading coefficients. That's the first 2 terms. And if you want to kind of get in your head what's going to happen, consider the degrees. We have a degree 4 over a degree 2. The numerator is larger than the denominator. In your head right now, you should be thinking, that means that we cannot possibly have a horizontal asymptote. Those only happen when they're equal or the denominator is bigger. We also can't have an oblique because the numerator is larger for an oblique asymptote, but only larger by power 1. This is more than power 1. So this is going to have end behavior that's not oblique and not horizontal asymptote. So what we're going to do is we're just going to take the leading coefficients, simplify them, and it's going to show us how this function is going to behave in its end behavior. All right, so when we take our leading terms, we have this x to the 4th over x squared. Power functions are always reducible by the variables. So we're going to say, all right, this is really just giving us x squared. That is how this function is going to look. So draw a picture of it. When you have just end behavior, draw a picture of it. So x squared is a parabola. It's upward opening because that is positive x squared and not negative x squared. So this picture is going to look something like that. Now some cool stuff can happen in the middle, like vertical asymptote or things like x-intercept, so y-intercept, stuff like that. Yep, this could have that. Actually, no, it can't have a y-intercept. So we're going to have a vertical asymptote at 0. We'll see that in just a second. But when we do this, we have at least a picture of the outsides. That's what's going to happen. It's going to follow x squared as we get to positive and negative infinity on the x-axis. That's going to happen. You can see that if you did like the limit idea. Take x, let it go really big. It's in square. You're going to get this. Take x, let it get really negative, and square it. You're going to get positive infinity again. It's going to look like that. Next thing we do is factor everything. So on our numerator, sort of like the last example, we think of this as x squared squared minus 4 squared. Well, when we factor that, that's going to give us x squared minus 4 and x squared plus 4. It is a difference of squares. While that's not factorable, that's an irreducible quadratic again. X squared plus constant, you can never factor that. X squared minus constant, you can always factor that. So we can factor that as x minus 2 and x plus 2. So we've taken this, we've factored it completely. A polynomial is always factorable as linear and or irreducible quadratic factors. So we have that. That's irreducible quadratic, that's linear. So we're good. On the denominator, well, we see that we have a GCF. Hopefully we see we have a GCF. We have a GCF of x. So we can just simply factor out x. Don't forget that that's possible. Always look for a GCF first. If we factor out x, then we get x minus 2. And I want to pause right here and tell you that the order of these steps is really important, especially these 3 steps. You can sort of do this one out of order sometimes. It's fine. You can simplify first and get the same end behavior. But this right here is very important. Factor, then define domain, then say what the domain causes graphically. So we factored. Now, before you cancel stuff out, you are going to define your domain. It's very important to not just, boop, oh, it's gone, because you're going to miss a hole. which is ironic, really, when you think about it. We're going to factor this, and we're going to define the domain by looking at your denominator again, and by the zero product property, setting every factor equal to 0 before you cancel. So x would equal 0, and x minus 2 would equal 0. You see, both of those are factors that if we allow them to equal 0, the entire denominator equals 0. You go, yeah, set that equals 0. Zero product property would say, okay, this would cause that, and this would cause that. And we're going to solve them. So x equals 0 is great. X equals 2 if we add 2. And here's what this means. Those are two issues that cause something undefined in our function. So as far as our domain is concerned, you might have wondered, why do we spend so much time on domain? For this, so that you understand that. We've been talking about domain for 2 classes now. So domain says you cannot allow x to equal 0 and you cannot allow x to equal 2. If that happens, you have problems. Now we're going to say what problems they cause. So we're not allowed to plug in 0 and we're not allowed to plug in 2. We're going to have missing things there, either a hole or an asymptote. That's how we're saying that we have a missing thing. Well, let's look back at the factor. So x equals 0 came from x, the factor x. Can you cancel out the x? No, you can't. All right, well, if you can't, then that defines a vertical asymptote at that value of x. And because that's an exponent 1, multiplicity 1, that's an odd vertical asymptote. So x equals 0 is the y-axis. So on the y-axis, we have an undefined value. We have a vertical asymptote. That's why I said earlier, you're not going to have a y-intercept. You're either doing this or this on the y-axis. You will not cross it. You won't touch it. Interesting. Now, at x equals 2, so let's look back at that factor. X equals 2 came from the factor x minus 2. So look back at that. Can you cancel out the x minus 2? Yes. But wait, what's that mean? When you can cancel out a factor that's causing a domain problem, a 0 on your denominator, that defines a removable discontinuity, or in other words, a hole, a missing point. So you can't let 2 go in there to your function evaluate because it causes this problem, but it's just going to be one point that's removed from your function. So at x equals 2, we have a hole. Now here's what I need you to do for a hole. So this is like your step 5. If you have a hole, you do one more thing. You simplify, which we've already done. You rewrite your function and here's the whole point of a missing point. This graph will look exactly like this graph, with one exception. This graph has a hole in this function. So here's what we're going to do. I know that I just told you, hey, you can't plug in 2. You still can't plug in 2, it's going to be a hole. You need to identify where that hole is. So in your simplified function, plug in the 2. We already know that we can't have it. That's why we define the domain that way. But you're going to show where that missing point is. You see, by saying you can't plug in 2 and saying here's the hole where I can't plug in 2, you are defining that you can't plug in that 2. You're saying there is a missing point here. So we have to evaluate our simplified function at the missing value to see where the missing point is. So we're going to plug in 2. Already know we can't have it. We're now showing that we can't have it and that it is a hole. So plug in, let's see, that would be 2 plus 2. That's 2 squared plus 4 over 2. 4 times, 4 plus 4 is 8. 4 times 8 is 32. That's 16. We are going to have a hole, a missing point at 2, 16. We're going to use that when we get to graphing. We're going to go over 2 on the x, up 16 on the y, and we're going to put a hole. We're going to say, oh, hey, our function is going to come to this hole and leave this hole, but it's going to be missing a point. Here's the whole thing about holes. This function is exactly like this function, except it's going to be missing that point. That's why we define it. So that's how holes interplay with these functions. That's just about it. All right, let's go ahead to our next example. So f of x equals polynomial over polynomial. First thing we do, because this is in standard form, we're going to find end behavior. Now, we might just look at this and go, hey, the degrees are equal. In your head, you need to be thinking, if the degrees are equal, I have a horizontal asymptote at the coefficients. So the ratio of the leading coefficients, that would be 2 over 3 or 2/3. So we should get out of this that y equals 2/3 is a horizontal asymptote. Now, we're always going to practice doing this end behavior. End behavior takes our leading terms, they're power functions, they should simplify, at least your variables. And this says, no matter what you do, your function as you get to positive and negative infinity is going to be 2/3. What's that mean? 2/3 is a horizontal line. Well, that would be a horizontal asymptote. So no matter what you do, you're going to get to 2/3. So we define that as a horizontal asymptote at y equals positive 2/3. Remember, you can cross a horizontal asymptote, but this function is going to tend to that value as we approach positive and negative infinity. Approach means as x gets closer to one value, the function does, that's a limit idea. As x approaches some value, the function gets closer and closer and closer to what value. In this case, as x gets to positive infinity and as x gets to negative infinity, the function is going to approach or get closer and closer and closer to the value 2/3, 0.666666. It's never going to touch it, but it's getting closer and closer. After that, man, we factor everything. So we're going to factor the numerator and the denominator. Do it as quickly as you can, effectively. We should know factoring pretty well. So I'm looking at that as -8 and 3 that multiplies to -24 that adds to -5. I always like to divide by my a and simplify. And I know that my numerator will be factored as 1x minus 4 and 2x plus 3. You can factor in whatever way you're comfortable with. I don't care. We just need to be able to factor. I probably check my work too. This would be 2x squared plus 3x minus 8x is minus 5x and then minus 12. So I know I'm right. It doesn't make sense to go any further unless you're absolutely sure about your factoring. If this is, just a little side note, if this is not factorable, then we have some issues. With a quadratic, you do the quadratic formula and you'd have to factor it with a quadratic. It's quite annoying. You're probably not going to run into that, but you'd have to do that. If it's over a power 2, then you'd go back to rational zeros theorem. You'd find a factor and 2 division, like symbolic division, to factor that out. So it can get very, very tedious. You're almost certainly not going to run into that in this class, but I want to prepare you for it so that we're not just limiting your ability. Okay, this 3x squared minus 11x minus 4, I'm going to do that right here. Take my -11 and -12. That's -12 and 1, that adds to -11, multiplies to -12. If I divide by my a and simplify, we're going to get 1x minus 4, and we're going to get 3x plus 1. And now, before we go any further, we're going to define our domain. So we take a look at our denominator, which is factored now. It looks great. We do not cancel those out. What we do is we say, all right, by the zero product property, if x minus 4 equals 0, we have an undefined value. If 3x plus 1 equals 0, we'd have another undefined value. Let's solve those. So these two values define our domain. We can have any value of x as long as we don't allow 4 or -1/3. Those would cause undefined values inside of our function. That's a problem. And now we're going to define what those problems create graphically. So let's look back at the 4. 4 comes from factor x minus 4 x minus 4, we're just going to ask, can you cancel that? Yeah. And if you can, then at x equals 4, we have a whole. In just a moment, we're going to simplify that and we're going to plug in 4 to figure out where the hole is, where the missing point is, where the undefined value is in our graph. Now, at x equals negative 1/3, that comes from 3x plus 1. Can you cancel 3x plus 1? No, there's nothing to cancel there. So what that says is that at x equals negative 1/3, we're going to have a vertical asymptote. Because it's a power 1, multiplicity 1, it's going to be odd. So it'll look like this or like this around x equals negative 1/3. So we said we can't plug in that value, therefore there's going to be nothing there, but it's a vertical asymptote in this case. We can't plug in 4, there's going to be nothing there, but it's going to be a hole in this case. In both cases, vertical asymptote or hole, there is a missing value of x. Now we're going to simplify this and say, all right, if we cancel out x minus 4, this function is going to look exactly like this function, except it's going to have a missing point. We need to show where that missing point is. Stop for a second and notice this though. Do you notice that this function has exactly the same end behavior as this one? So if you divide, here's power 1, that says horizontal asymptote at coefficients, that's 2/3. That's exactly that. Do you notice that this has exactly the same vertical asymptote as this does, negative 1/3? This says something. And sometimes this benefits you. If you have a hole, sometimes you can find your end behavior easier if you cancel out the hole. The problem is you don't know if you have a hole until you factor it. So you might want to risk that if you think factoring is going to cancel out a factor for you. Then you might want to find your end behavior later because it's just a little bit easier and your vertical asymptote will still appear. Here's the one thing you can't do. You can't go, oh, I'm just going to cancel it and this doesn't matter. This absolutely matters. And you need to evaluate your simplified function to find the value of that hole, to find the value of that missing point. So we're going to take and we're going to evaluate this for 4. So we're plugging in 4 now. If I evaluate 4, that's 2 times 4 plus 3. Let's see, that's 8 plus 3. That's 11 over 13. So we are going to have a missing value on our function. At 4, 11/13. You are always going to do this. Here's why. I've seen a lot of students go, oh, I have a hole at x equals 4. And they go to the x-axis and they put a hole. That is not at all what this is saying. This is saying that at the value 4, 11/13, so almost 4, 1, there is your missing point. Your function is going to come to that missing point. It's going to leave that missing point. It's going to leave that point empty. This graph will look exactly like this graph, except it'll be missing that point. So how do we do it? We graph this and we take out that point. That's what the hole does. And it gives us that graph, and that's kind of cool. I'm going to come back with 2 more examples where we deal with some oblique asymptotes, and then we'll be done. All right, here we go. Let's take a look at g of x. First thing that we do with standard form polynomials and rational functions is find end behavior. And so we're going to do that right now. If this had all been factored, we would fake distribute and find end behavior first anyway. So that's usually the first thing we do, almost all the time. So we're going to take and say, hey, g of x in its end behavior is going to look a lot like x cubed over x squared, our leading terms in ratio, and simplify them. This is just x to the first power. You know, wait a minute, x to the first power is a diagonal line. And if you think back to that video on oblique asymptotes, if your numerator is larger than your denominator in terms of degree by exactly 1, you will have a slant or diagonal or oblique asymptote. We have to find that. So you have an option here. With oblique asymptotes, there's kind of 2 cases. One where you can cancel out a factor and one where you can't. So if you know that you're going to be able to cancel out a factor, you might try to factor first. And I'm going to show you that in that example. If you don't, I have no idea. Well, actually I do, but you might try to just do your long division to figure out your slant asymptote. It's kind of up to you. Try both ways and see which one works for you. What I'm going to show you is both ways. So first way, if you don't know if you're going to be able to cancel something out, you're just going to have to straight up do long division right now. As soon as you determine, hey, my end behavior is x to the first power, pause. That's not horizontal. That's not just x equals power 1. You need to go a little further. So we're going to take and we're going to divide x cubed minus 8 by x squared minus 5x plus 6. Remember that synthetic division does not work here, but we only have 2 steps we need to do. We take first term divided by first term, we distribute, we subtract, and we're pretty much done. We don't have to bring this down. I do not care. All we need to do is take first term divided by first term. 5x squared divided by x squared is just simply 5 plus 5. Don't worry about distribution. This right here, this is your oblique or slant or diagonal asymptote. So we'd say we have an oblique asymptote at y equals x plus 5. I only did one example in the oblique asymptotes. They don't actually happen all that often for us, but you only need to do 2 steps on your long division. So as soon as you determine that is 1 degree more than that one, do your long division, do only 2 steps. Divide first term by first term, we did. That would be x. Distribute. Subtract term by term. 0 minus negative 5 is plus. 0 minus 6 is negative 6. And then do first term divided by first term. 5x squared divided by x squared is just positive 5. X plus 5, you're done. You don't even really need to subtract this one. This is your oblique asymptote for sure. That's going to help us graph in the next video. The next thing we do is we factor everything. So that can be sort of difficult if you don't remember some of the factoring techniques, like x cubed minus 8. Well, that's a difference of cubes. Difference of cubes works kind of funny. What we do is we take first term minus second term, so x minus 2. And then inside the next set of parentheses, you take first thing squared minus plus multiply them together plus second thing squared, which is 4. We've done that a couple times, but not very often. So it has this formula you might want to look up, this pattern that says you have the same sign and then opposite signs and then always a plus. So first minus second, first squared plus multiply them together, and then second thing squared. That would be 2 squared, this thing squared. This comes from the 2 times the x, and this comes from the first thing squared. That's how that works. On our denominator, well, we have a fairly simple quadratic that we can factor. That's negative 3 and negative 2. Dividing by 1 doesn't change those, so this is a pretty nice one. X minus 3 and x minus 2. After that, man, we go right to defining our domain. So zero product property says x minus 3 equals 0, x minus 2 equals 0, x equals 3, and x equals 2. Those are problems. So our domain says you can't have that. That bad. Now define what they create. If you can cancel out the factor that's giving you your domain restriction, that's a hole. If you can't, it's a vertical asymptote. So we look back at 3, comes from x minus 3. I cannot cancel that factor. There is no x minus 3. That's an irreducible quadratic. You could check it real quick if you want to. But if you tried quadratic formula, it's going to give you 4 squared minus 4 times 1 times 4. 4 squared minus 16, well, that's going to give you negative 12. And you can't have that, an I, inside of your polynomial if you want to graph it. So we know that's irreducible. So this comes from this factor. You cannot cancel it. Therefore, at x equals 3, we have something we can't have, but it's a vertical asymptote. And because that multiplicity is 1, that creates an odd. At x equals 3, we're doing this or this. Odd means opposite infinities for vertical asymptotes. Now, x equals 2 comes from the factor x minus 2. So we ask, can we cancel x minus 2? Yeah, sure enough we can. What that means is that we can't allow 2. It's going to create for us a missing point, a hole at x equals 2. We're going to define where that is exactly later. So we know at x equals 2 there's going to be a hole. We're going to have to define where that hole is. So now we're going to simplify this. And I want you to notice something. This is, I said you can sort of go back, like sort of out of order with oblique. If you knew that that was going to cancel, which most of the time we don't know that, you can still find your oblique asymptote from here. If you wanted to divide this by this, you could even do synthetic division, and you would get the same thing. So synthetic division would say positive 3. Remember, positive 3 would act like an intercept here. Positive 3 would be 1, 3, add them together, 5, and that gives you right there. The remainder doesn't matter at all. This would be x plus 5, just like that is x plus 5. It actually works. If you want to do long division of polynomials here, you'd see the same exact thing. But your end behavior cannot change. If you simplify your function, you're going to have the same end behavior. 2 and 1 still says numerator's higher by 1. You still have an oblique. I even showed you right there the same oblique. Still the same vertical asymptote. You'd still have the same x-intercepts. They're not going to be any here. So all of that is possible after you simplify. It just depends on what you start with. So if you start like this, it's sometimes easier to find end behavior just right off the bat. All right, so now that we have a simplified rational function, we're going to plug in that 2 to see what we get. So if we evaluate g of 2, that would be 4, 2 squared is 4, 4, 2 times 2 is 4, and 4. So 4 plus 4 plus 4, I think that's 12, over 2 minus 3, which is negative 1. So we would have a hole at 2 comma negative 12. This function and this function are identical. So we graph this one and then just remove 1 point. We have a missing point. The function will hit 2 comma negative 12. It will go right over it and then continue. It will miss that point. That's why we have this domain restriction first. Do not cancel out first. Define your domain first and then say what that does for your graph. That's what we're doing. All right, last one. H of x equals nasty stuff. Well, we do end behavior first, and we just look at the degree. We go, okay, hey, that's degree 2 over degree 1. The numerator has a degree 1 larger than the denominator. We will have an oblique asymptote. Can we do long division of polynomials? Of course we can. Could you factor this maybe because it's easy to factor? Yes, but you'd have to define your domain first. So make sure you do that. So I'm going to show you that right now. This one I showed you this way to say, what if I don't know I can factor it like I showed you over here? I don't know. Then do long division. If you know that you can factor that, maybe spend 10 seconds trying. You might want to do that first. So I'm telling you, this is a little malleable. These 3 steps are not. And you have to evaluate for your whole if you do have one. So we're going to show that here too. But what if you know you can factor that? For instance, I've taught you well. You're all very smart. You're very good at factoring. If you go, yeah, I can factor 7 and negative 30, that's pretty easy. I mean, that's negative 3 and 10. I know that adds a 7. That multiplies to negative 30. I know if I divide by my a, and I simplify. So 2 goes into 10 and, and I simplify. 2 goes into 10 5 times and 6 3 times. 3 goes into 3 1 time and 6 2 times. So I know that my numerator can factor as 2x minus 1 and 3x plus 5. You go, Leonard, you tricky guy, what'd you do? Well, I knew it was factorable. Number one, because I made the problem up. But number two, because I'm really good at factoring, because I made you practice this so much. You guys are good at it too. So maybe try to factor it. Why? Well, because now we can identify right now that this, which is completely factored, you can't factor that anymore. That right there is going to create a whole for us. So we've kind of shortcutted the whole long division of polynomials because of this. So we go, all right, well, what's that going to do? Well, what that does is that says, okay, set your denominator equal to 0. And we'd say our domain says you cannot allow -5/3. All right, let's determine what that does. If we look back at 3x plus 5, the factor where we got -5/3, you can cancel that. That means that at x equals -5/3, we're going to have a whole. Now, we're going to have to plug that in and figure out where that whole is. But notice that we can simplify our function now. We just get 2x minus 1. Now I'm going to pause because there should be just this question in your head. Like you should be going, but wait, you said that's 2, that's 1. You should have an oblique asymptote. Where'd that go? Oh no! This is your oblique asymptote. This function rides that line 2x minus 1 forever. It is an asymptote. It just happens that this function is going to be on it the entire time. The only difference between this graph and this graph is that this graph is going to have a hole somewhere on that line. That's it. So can you intersect an oblique or a horizontal asymptote? Yes, I made a strong point that you could. In fact, this function is on that oblique asymptote the entire time. It is that graph. If you graph 2x minus 1, then you're going to get this function. The only thing you need to exclude is 1 point. You need to exclude -5/3, comma, whatever we're going to get. So we're going to evaluate right now. So if I plug that in, -10/3 minus 1. That's going to give us -13/3. And that's where our removable discontinuity is. So here's the main point in this example. If you were to graph this function and remove this point, you will get that graph. That's what this means. So can you graph 2x minus 1? Easily. Go down 1, that's your y-intercept, -1. Go up 2 over 1 to the right, that's your slope. Take out exactly that point, and you will get exactly that function. I hope that interests you. I hope that's fascinating. If you want, I just have a minute or so. If you want to do this differently, if you don't like the fact that I went out of order because you're like me and want everything in order, I get it in the same way. You said, I just really want to do end behavior first. That's totally fine. And if you want to do that and go, hey, look, this degree is 1 more than that one. If I thought about my power functions, and simplified that, you're going to get 2x. Is it a coincidence that that 2x is that 2x? It's not a coincidence. That's the first thing that you're going to get when you do long division. Think about that. First thing you do with long division polynomials is take first term divided by first term, isn't it? It's going to give you exactly that. By the way, you could do this with synthetic, but you'd have to use -5/3, which is a little bit awkward to use. So I'm just going to do this because it's easier. If we divide 6x squared by 3x, we get 2x. If we subtract, we get 0 and we get minus 3x. I don't even care about the minus 5. Now, you can put it, and it's going to show you something else, but I really don't care. Because if we divide negative 3x by 3x, we get negative 1. If I distribute, which I don't even have to do, this right here, as we know, that is your oblique asymptote. We'd say oblique asymptote happens at 2x minus 1. Later on, we'd go and cancel this and go, wait a minute, that function is 2x minus 1. Can the oblique asymptote be your function? Yes, but only if you're missing a point, which is what that tells us. That's the point. So if you want to do this, this would still bear out as an oblique asymptote. Later on, you would factor this and cancel it and go, okay, my oblique asymptote is my function. It's just this function has a hole in it. So oblique asymptote is your function perfectly. You just take out one point, which we have found anyway. I hope that makes sense. That's not a hard example, but quite advanced because you have to understand a lot about it to get that. So I hope I've made it make sense. I hope I'm explaining this well enough for you. Next video, we are going to do everything. We're going to graph a whole bunch of examples. It's going to be a very, very long video, and I need you to watch it. It'll be fun. It'll be good times, but it's going to put everything together. It is one of the cornerstones of this course, and it leads you into Calculus 1 and graphing functions very, very well. So I hope you're doing well, and I hope to see you for the next video.